So you've already heard, okay, so this is me from the University of Constance. Hi. Thank you for the very kind introduction, and it's a great honor for me to speak here. So it's the first talk I'm giving about my work in front of a bigger audience, so outside of the lab. I should stand here. Okay, thank you. I want to see my notes. They are.
It's okay.
There. Okay. So probably you all know about this method. You have heard it several times. The very important step is diffraction for destruction. So we have many crystals, or crystal volumes for that matter. There was a recent paper, had one crystal and shot many times at the same crystal, not only different volumes of the same crystal. We therefore have many diffraction patterns. Therefore, we have many indexed and integrated intensities for each pattern, and then we merge the intensities. So basically like this. So it's more complicated. This is just a very rough overview what we are working with. And I want to, so just like James Holton, tell you a bit about statistics. So only the very basics, but they are important. So it's important to know the difference between accuracy and precision. So precision is how well the measurement reproduces itself, or how well the measured values agree with themselves. So, for example, if you fire a gun, you can imagine this experiment like you fire a gun and you try to hit this aim, and this is where you hit. And you can say, okay, well, it's not very precise. I'm quite far off several times, but it's in the mean value is quite accurate because it's not far from the true value where you were aiming at. In the next case, it's very accurate, it's very precise because all of the shots, they are at the same positions, but they are far from the true value, so the accuracy of this shot is bad. In the case of a gun, this doesn't matter because you can just adjust the aim of the gun, and then you will, in the future, you will hit here. We need one more step to have a very rough idea of the crystal data or the free electron laser data. For free electron laser data, we have many measurements. So in this case, it's 4, each indicated with a different color, and each has its own systematic errors. Or you could view it in another way and say each measurement contains information that you don't want to have. You want to know the true value, but you measure also other things that are in the way. And what you want to have is something like this, and yeah, hopefully we can all contribute to get the measurement into this direction by correcting all the systematic errors that are within this measurement to increase precision and hopefully also increase accuracy of the measurement. So this is just an example. This is a histogram or heat map of the significantly positive intensities and the positions on the detector. So you can see here something like a powder pattern. This is what you would expect. But you can also see those spots. Yeah, we heard from the cheetah talk that this is an ongoing investigation, and this may be due to either those spots were flagged and removed, so this error was removed, or they weren't flagged and we have those wrongly zero intensity reflections within our data. So I didn't look at it further. It's just to get an idea of what are the systematic errors. We have also heard about other things just before. So we also have heard about partiality. We have seen many models for the partiality, or heard about many models, and but we haven't seen a video. Is it there? Okay. Just to show you, if we rotate the crystal, then some intensities go and some new intensities show up. Okay, it's nothing new. Yeah, okay. And if we just take the orientation of the crystal as determined by Christopher and compare these intensities to an external reference, so sheet, then we can somehow plot the partiality depending on how well they agree, the intensity, and how well the Bragg's law is fulfilled. So this is relative. So here 5% disagreement, and here 100% agreement. And what we can see is, and what is very surprising on first thought, is that we have two peaks, and each at about 1% off. And this is probably due to 1% systematic errors in the cell orientation. But I really don't know what causes this, but it's just to give you an idea of another systematic error. So, and to fix those errors, we need to find them first. And to do this, we need to find the variable that this error is dependent on. So, for example, in the partiality would be dependent on the resolution and the distance to the Bragg sphere, and some other errors may be dependent on the position of the detector. And after we find the variable that this is that the error is dependent on, we need to find the law behind that connects all of them, and then we can revert the error, or in other words, filter out the information that we want to have and remove the information that we do not want to keep. Those variables may not always be measurable or directly measurable, so they are hidden variables, and we need to determine them, the most likely variables of those kind. And this is sometimes then referred to an expectation maximization. I now want to come to the twinning problem, which was also a systematic error in the free electron laser data, but it was one that didn't average out in the mean. So most of the other errors, they just average out, and you measure enough, and in the end you have, in theory, you have a perfect data set, because everything averages out with many data. So you don't want to measure many data, but it's even worse if it doesn't measure average out. And for this I want to give a short introduction what twinning is. So for example, if this would be the diffraction pattern of the crystal viewed from one side, and this would be the diffraction pattern of the crystal viewed from the other side, or by 90 degrees, depends. And if they give diffraction patterns that have spot locations that are in exactly the same position, there is no way for the indexing to know which one of the two to choose. And if we then add both together, then we get to something like this. If they have a different fraction or different contribution, we get to something like this. Or if both of those crystals, or if we have two crystals and they are both sticking together, then we also get something like this or this. This if they have equal volumes, and this if they have different volumes. So in free electron laser data, we normally deal with computational twinning, not with real twinning, because the crystals, they are too small normally to form twins. They still maybe can, but it's much more unlikely. And but the bad thing is that we have many crystals, and we don't have the relative orientations of those crystals. So each time a space group allows, or better yet, a point group allows diffraction patterns to be indexed in different ways, they will be indexed in different ways, in each indexing mode, just randomly. And this is the case for roughly 1/3 of all projects. And therefore, if we just merge everything together and do a Monte Carlo integration, merging, we will have computationally twinned data, and this data will behave exactly as real twinned data and is harder to solve. So we don't want this. And the basic idea which came from Kai, and which is at the basis of this problem, is that the mean agreement between shots of the same indexing mode should be high, and the mean agreement between shots of differing indexing mode should be low. And we are using the correlation coefficient as a measure of this agreement between shots. This may not be the best solution, but it's very easy to calculate. It has well-known and nice properties. It's most importantly, it's scale invariant. So it doesn't matter if one image in total has a higher intensity than the other. They can still have a very high correlation, or even a correlation of 1. So we don't need to do the scaling before we can apply the algorithms, which made our lives much more easier. It assumes a Gaussian distribution of the compared parameters, which are the intensities. So maybe there's a better solution, which assumes maximum likelihood or gamma distribution. But I think as long as, and especially in our case, probably the Gaussian distributed errors, they are prevalent. So this is probably a very, very good solution or measurement for the agreement. So the first step that we took into solving this problem was using a classical multidimensional scaling algorithm and interpreted 1 minus the correlation coefficient as a distance. So we wanted to find a position in a space of all the spots, for which the distance between the shots agrees most with 1 minus the correlation coefficient. This means that, or we thought about this, that if the correlation is high, then it's close to 1. Then the distance should be low, because 1 minus 1 is 0, and then we want the shots to be together at the same point. And if the correlation is low, so like 0, then we expect a large distance. And we minimize this function. You can use any algorithm to minimize this function, but we used LBFGS to minimize this function. And we get to an arrangement like this. And this takes around 5 minutes for those 15,000 shots that we have here works up until like 400 shots to some extent, and in this arrangement around 1% were wrongly assigned. So this is simulated data. That's why we can color code each indexing mode. It works just as well for real data, and we tried to have an error in our simulation that is as big as in the real data. And to achieve this, we first did multiply each intensity, each true intensity, with a value that is randomly distributed between 0 and 1, and then added a random error equally distributed around 0 with 3 times the mean intensity as sigma. So it's a huge error that we had to add to the true values from a reference to get an error that is at the same order as from the experiments that we are doing. So we have huge errors in there. As we saw, this arrangement is not that good, and if we didn't know the colors, it would be very hard to find this line, because they are separated, but the separation between them is very faint, and you cannot find this separation. So we thought about a better way to represent the correlation coefficient, to find a space that is more closely related to the correlation coefficient. And it turns out the dot product is very much suited for the correlation coefficient. So again, each point is represented as a point, or each shot is represented as a point in 2D space. You could also imagine this as a shot with only 2 intensities. So we try to represent the shots which have a very high space but a sparse space of all the intensities in a 2D space. And this works much better and has some very nice properties, and some of them I want to highlight. So we always get a 90-degree separation of those two, because if you think about this as one shot and this as the other one, just 2 shots, then, or maybe, just as 2 shots for the beginning, then if we do the dot product between this and this one, it's 0, because 90 degrees, and the dot product is 0. And if we, for example, take the dot product between this shot and the other one, that is in the same cloud, so to say, it is here, and the correlation is whatever, 0.3, for example. So this space that is formed by the dot product is more accommodating for the correlation coefficient, and this converges much faster and is giving a better assignment. But this is not the best thing that we could come up with. We thought about this arrangement that you just saw. Sorry, I go back there. And we think about what is all in this plot. What do we need? So what we see here, there is more information in there that we want to know in this special case. In this special case, we have an either-or decision. Either it's indexed in the one indexing mode, or it's indexed in the other indexing mode. But what the plot could actually give us is like a continuation of indexing possibilities. But this is not the case. This would only be the case if we had physically twinned crystals with differing contributions of the two indexing modes, so with differing volumes of twinned crystals. But this is not the case. So what we first thought is, and then we have also this direction here, so that the how far it is away from zero. So it's nice to see that those probably have a very low coefficient, very low correlation, and those are correlating well. But we don't need this. So we first, if we fix the length of the correlation coefficient to 1 and allow only the angle 90 or 0 degrees, and we reformulate the thing, we get to algorithm 3. Because if you only allow either 90 or 0 degrees, it means either it contributes or it doesn't. So either it's 0 or it's 1. So each shot gets only a 0 or a 1. Or in other words, is assigned to a group or to the other one. And this is going back to the very basic idea that we need to find two groups that have a very high correlation within and a low correlation between them. And for this we use a k-means clustering algorithm. We didn't know at the time that it was called that way, but as k-means clustering is very powerful and a subset of, or an easy case, so to say, of expectation maximization, I want to show in a little bit more detail how it works. So for each of those spots, each of those spots you can now imagine as an image that has two measured intensities. This would be one intensity, and this would be the other intensity. And we have two different real images in green and random arrows. Just judging by eye, we can hardly find those points. So if I didn't highlight those points, and yeah, it would just be random and we couldn't find the points. So you wouldn't know where they are, even with your eye, which is very powerful for 2D images. And what we do, we start off with random assigned, we just randomly assign each one to one group, and then make the mean of all those of each group. That's why K means clustering. We make the mean of a group, and then we reassign every shot to the group that it's most closely, that the distance is lowest. So this shot would be there, this shot would be there, this shot would be there, but this shot would go to this group. And this is basically a division at this line. So everything above here goes into the blue group, everything below here goes into the red group. And we repeat. We make a new mean, make a new reassignment, split at this line. Repeat. And we are finished. And we are very close to the true value with this algorithm, very fast. And this can also be done with a little bit, with just a little translation to free electron laser data. A little translation because not every not every intensity is on every shot, but in maybe 1% of all the possible intensities are on one shot. But it works fine. We start from random assignments and reassign each shot to the group it agrees to more until it converges. And this converges usually very fast. And this is a sample run. This is 15,000 crystals already indexed. This is the data set of you that we got from you finally. Yeah.
Oh, it's not mine. It was before I joined. But anyway, it's PS1.
But we communicated with you at that time. So, okay, sorry.
You're welcome.
And we only need 2 iterations over all the crystals. So each crystal is reassigned to the group that it agrees to more twice. And after that, it's already converged. And what we see in blue is the correlation coefficient to the group that it's coming from. And in yellow, we see the correlation coefficient to the other group. So in the beginning, those 2 seem just random. They are random in the beginning. So in the beginning, both the group that it's going to and the group it's coming from, they are both the same. But after some time, it's like if you put a round thing like this or an egg, and you try to put it on a table with a point, it will fall down. Even if you try to balance it very well. In the beginning, it seems it's very good balance, but the balance, it decreases over time. With each reassignment, the balance is broken even more. And after that, the reassignment gets better and better with each step, and we can deduce the true groups that they are there. So this takes about 5 seconds on my laptop that is here. So general strategies to increase this power of discrimination is to increase the number of comparisons that can be made. And one way is, of course, to apply the known symmetry and point group symmetry and space group symmetry, and also assume the mirror. And the other one is to use, if you know it, the known twinning operator. Because if you know the twinning operator, you can effectively double the amount of shots that you have. Because each shot has a shot that is the exact opposite. That is the same shot in the other indexing mode. Just by applying the indexing, the twinning operator to the shot, you get the shot indexed in the other indexing mode, and if you use both of them, the decision will be better because you can compare to more shots. Because everything is so noisy, you need the mean of many things to average out the error. So in the end, if you have those 2 groups and you know the twinning operator, of course you can apply it to one of the 2 groups and have then only one group left which has a high correlation within, and you have solved the indexing ambiguity. If you do not know the indexing operator, the twinning operator, you can just test which twinning operator will give you the highest agreement between the 2 groups. If you do not find an indexing a twinning operator that will lead to a high agreement between the 2 groups, you may have different kind of data, different things within your data. A difference or a variance in your data which does not come from twinning. Okay, now I want to go back. And there I want to conclude the indexing ambiguity. So it was implemented in Kai implemented it and tried to distribute his own program, but it didn't turn out that well because people had troubles using it and no one knew about it. And so I went to Hamburg and had a nice time working together with Tom White, implementing, or actually he implemented it into Crystal, and I helped him. And yeah, so this is mostly solved. The only thing that could possibly be better would be the function of agreement, which could be tweaked maybe a bit, and the what we could call a seeding, so that the initial groups that we try to introduce a stronger bias in the two groups at the beginning. So right now we are just having random assignments of the two groups, but we could maybe by using one frame as a reference for all the others, introduce a stronger bias from the beginning on, but only small details, I would say. So on the way to good data, we are all on this way. So we want to have good data. We want only to have the information within the data that we are interested in, which are structure factors of those kind of experiments that we are doing. And for this, we need to eliminate all of those errors. And I've learned it's not only what I have here. I knew that, but now I know more to put on that list. You've heard about all of those things, and probably one of the last things. So they are all bigger, and there are other ones that are even bigger, maybe. And that's why if we want to be able to find an isomorphism within our data, we need to get rid of all the others, because otherwise we cannot find them. And why do we want to get there? Because there it will be starting to get interesting from a biological point of view again, because we can do maybe time-dependent measurements, or we can have two different conformations, like in the lysozyme case, within just one crystal batch, and we want to separate those two. And the error that those different conformations introduce, it may be very small, or in the case of lysozyme, it is very big. So we may be able to even find it with the data that we have. But this is what I'm working on right now, or what I want to work right now. And here is people I want to thank. So I want to thank Kai Diederichs, my mentor in Constance, for the very great ideas, the discussion and educations that I had there. Thomas White for the collaboration at the DAISY, and Felix Baumann for the, which is a former colleague of mine, for the discussion about the Canadian question. Thank you very much. So I see I have much time left, and I appreciate all of your questions, but if they are over, I can also show 2 videos of the algorithms and work. Okay.
Do you have any questions? I have a question for you. It wasn't mine, but I can't remember the name of the person that said this. Do you think the data would improve if you threw away the region where the two data sets overlapped in their correlation? You said there's 1% misaligned, but when you look at it, what if we just completely ignored all those patterns?
So you are referring to the algorithm 2?
Yeah, there. No. Go.
Yeah,
the last one.
Wait, this one?
No, at the end.
At the end?
Yeah.
So at the end.
The last one, the blue and yellow.
Okay.
Yeah. What if you cut away the region where they're closest and throw away, I don't know, 10%?
So this is a little bit more difficult to interpret this plot, because this is now this is now over the course of the clustering. So what you see here is not yet clustered.
Right, but at the end,
Okay, at the end, yeah.
I mean, you can see it's converged, or diverged nicely, but they're still quite widespread.
Yeah.
Wide spreads. Would we gain anything by throwing away the part where the yellow and the blue dots overlap? In the very last bit, in the 30,000.
So here normally when the yellow and blue overlaps, it's from different frames, from different shots. So if here, for example, the one shot, for example, if we take the last one may be here, maybe here, but it may be here for the other one. So they don't overlap. So if they overlap, we would have switched them. So here, all of the blue ones are above the yellow ones.
I see.
In total. So there is none of those cases. But we can use another criterion to get rid of shots that don't correlate well. And this is if they, we can determine for each correlation coefficient what the error of this correlation coefficient is, because it's all worked out by mathematicians long ago. And if the correlation of one shot to the group that it's in is insignificant, so it's very low and it has a higher error than the correlation coefficient, we can throw it away. This is for sure, because if the correlation is lower than the error of the correlation, then we can also make this more stringent.
Okay.
And you probably will gain something up until to a certain value, which we don't know, but it's for certain if it doesn't correlate significantly that you will gain something. Yeah?
Did you correct your intensities by the calculated partiality?
No, so...
It would be much better to do that.
Yeah, of course. But for we tried to. The beauty of these algorithm is that you don't need to do
it. Why not make life easy for yourself?
Yeah, we did.
Because I think correct partiality isn't that easy.
Collect with your calculated partiality, then the reflection would, it'd be much easier to separate the two.
Of course, yeah.
So why don't you make your life easy?
Yeah, we made our lives easy by not doing it. No.
We don't have good partialities.
Yeah, if you try to do partiality, I was going to have to try and maximize the agreement between, so I always have to all the algorithms so far, between the observed intensity and your sort of mean intensity. If you haven't already done this, the mean intensity is after a
chicken and egg problem.
Therefore,
exactly. Yeah.
So if you do a partiality refinement before this, you're going to have made your intensity wrong.
Yeah, exactly. It's a chicken and egg problem. And in addition to it already being difficult, there's a chicken and egg problem involved when we have indexing ambiguity. Because to determine the partiality of our data, we need to maximize the agreement of the data within using the partiality.
No, you can just index it. Get your reflections, index them. You won't get very accurate calculated partiality, but be good enough.
No, exactly. This is not the case. So I've showed this plot here. So these are the apparent partiality depending on the compliance with the Bragg's law. So this is like a measure how far they are away. And if we just
you index an image, and then these are the partial.
But no, I indexed many images, like 100,000.
Okay.
And this is the mean that we see there. So there's a huge error in there, which I can show you at the very end. So this is the raw data, and if we make the mean, we see the plot that we just saw.
Well, you've got some external. I don't know what this is about.
So I use an external reference
to get this from.
Yeah, from synchrotron data.
So you're cheating with that.
Yeah, of course we need to cheat. We need to understand the problems.
Yeah, I understand the problem. I don't need to cheat though. But if you don't have, normally you don't have a reference, so what's the point?
point is to first understand what's going on.
Well, I know what's going on. You've got two possible ways of indexing.
Yeah, but that's yeah, okay, we solved that one. This one is easy. Compared to the partialities, this is probably easy, because the partialities are depending on your cell orientation. And the cell orientation is not that well defined when you index.
It doesn't, the partiality will not change which way you index it. Because the spot, the simple value spot is in the same position.
I'm not sure about that one, but
I'm quite certain about that.
Okay, maybe, but
It's obvious.
But
hang on, when you estimate the partiality of a certain spot, that's based on the intensity you measure of that spot, right?
No, the calculated partiality is not based on the intensity you measure. It's based on the position of the Ewald's
the spot
depends on the indexing process.
Right. But the indexing is based only on the positions, and so the position, the indexing of an image will have a systematic error. It is described in the paper of.
I don't care what
Wolfgang
paper is described. The spot will be in the same position, which no matter whether it's A or B. Because
No. Okay.
The simple ambiguity.
So leave out the ambiguity. Leave out the ambiguity.
Okay.
Just leave out the ambiguity for 1 minute, and just have an image without any ambiguity, and index that one with MOSFET, whatever, or with XDS. It doesn't matter. They all try to push all the intensities they see on this frame as close to the Ewald sphere as possible.
The position of the spot depends on the indexing processes. They're not pushing things close.
No, but they need to refine the position.
No, it's not. Before post-defining.
No, okay, so for indexing, you need to determine the cell parameters.
Well, part of the...
You need to define the orientation of the unit cell. Yeah.
But look, you can index it. You can index in two different ways, and therefore the spot will be the simple lattice point will be in the same position.
Yeah, it will have the same HKL value, but it will have a
same partiality.
Yeah, it will have the same. The partiality is not dependent on the indexing, but it will have a different cell orientation. You do not know the exact cell orientation.
Partiality is the same, and that determines your degree of partiality. You measure the intensity.
No, you have an error in the cell orientation when you index.
Yeah, so the zero, it's like in Tom's example, iteration 0 is independent of intensity, right? Then iteration 1, 2, 3, 4, 5, etc.
Yeah, of course, yeah.
So the impression I get is that have you tried doing this procedure, applying an iteration 0 partiality correction before you do the disambiguation?
Yeah, so it will still work, but it will lower the quality of the data. If we just say, okay, we have those kind of cell orientation, and we try to reverse the effect that the partiality will have based on the estimate of a partiality based on those wrongly determined cell parameters, it will even decrease the data quality. Because the estimate of the cell orientation has a systematic error, and this is what this plot can also show. It has a systematic error of about 1 degree. So just 1%.
If we all agree that the partiality problem can be solved, I don't think that's what this talk is about.
No, it's about solving the indexing ambiguity. It's about something that has been solved, and the other things we are just thinking about, so I cannot offer solutions for that. Of course, we have tried things.
Perhaps it's just the fact that it's so standard.
Yeah, maybe if there are some other questions for my talk, and after that we could start the panel discussion.
Can you segue smoothly into the panel discussion?
Or maybe you want to see the videos about.
while he's getting the video set up, could we have all the speakers from today and from tomorrow, Michael, kind of move your way to the front, and then I just want it to be easy to record the discussion. I want it to be almost like a panel, but I didn't want to move too many tables around. But if someone has a better suggestion. Sure do.
So this would be for algorithm 1, so that you get an idea how they sort each other out.
Sorry.
This would be algorithm 2. Quite funny how it but it's much faster, as you can already see. Each image is one iteration. Okay, that's about all.
For algorithm 3?
So there's no video because of no positions that you can see, only 0 or 1, and you can see how 0 and 1 changes, but instead you cannot visualize it nicely. I'm sorry.
Well, thank you for those.